So what you need to do is parameterize S1, the base of the half ball. Now, it might seem simple enough because it's just the unit disk. So if we're looking at this from below, this is what we're seeing. So it's like the negative z-axis is coming out of the board, positive z is pointing into the board. But the normal must be pointing this way. Now, the usual way of parameterizing a unit disk would be to take x equal to u cosine v, and y is u sine v. And let u go from 0 to 1, v go from 0 to 2 pi. Okay, now, but what will happen if we go ahead and use it? Our unit normal vector will turn out to be 0, 0, 1, pointing up. Also, z is equal to 0. Okay, so that's not going to work for us. We need it to be pointing down. We need it to point outside of a solid. So here's something we can do instead. We can let x be equal to u sine v, y is equal to u cosine v, z is equal to 0. Right. Same limits on u and v. Since the region is completely symmetrical with respect to x and y, there's no problem with interchanging roles of x and y. So if you fix a particular value of u, you would be starting from this point and tracing clockwise around as v changed. Whereas regular parameterization for polar coordinates starts here and traces in this direction. Okay. Now, so this is one way to do it. Another way to do it is if you interchange the roles of u and v, then that would work also. Okay. So we go ahead and compute our vectors, ru and rv. So we're going to get derivative of this. These components with respect to u. We get sine v, cosine v 0. Rv is going to be u cosine v minus u sine v 0. So then, if we take a cross product of these, what are we going to get? Well, for a first component, we'll get 0. For a second component, we'll get 0. Third component, we'll get minus u sine squared v minus u cosine squared v. So that's going to be minus, that would be u, pull out a u, times 0, 0, minus 1. So it is pointing downward.
Here, you have it written sine u and cosine u. Taking the derivative instead of
v. Yeah, those should be v's. Okay. And everything else is fine. That's page 3. I had u's instead of v's. It should be v's. All right. Okay, so this is a parameterization that works for us because it has the normal pointing in the right direction. All right. So now what we can do is we can take this. Now that we have a parameterization, so we'll go from my outer 0 to 1 in u, and 0 to 2 pi in v, and what we need is the vector field f. So that's going to be I'm going to write this in terms of x, y, and z still for convenience. Squared dot product with u times the 0, 0 minus 1. So dot product with the normal du dv. All right. Now, the nice thing is, it doesn't matter how painful these would be to integrate, they're gone. Because when we compute the dot product, we have the zeros here. It's going to wipe it all out. So again, 0 to 1, 0 to 2 pi, we'll have minus u times all this, x squared z plus y squared, which we need to fill in our parameterization for. So x squared, that's u squared sine squared v, times z, but z is 0. So that makes it even simpler, plus y squared, so that would be u squared cosine squared v, du dv. So that's gone. So now we have 0, 1, 0 to 2 pi. I'll pull out a minus. So now we have u cubed cosine squared v of this should be dv du, dv du, because u is my outer. Okay. So now that is what needs to be integrated. So a little more work than the last one, because now you got to rewrite cosine squared v. That's the same as 1 plus cosine 2v over 2. So now what you're going to have is v over 2 plus sine 2v over 4, evaluated from 0 to 2 pi du. Don't get the minus. Now, when we plug in 0 and 2 pi, that's just going to be 0, nothing going on there. And then we have 2 pi over 2, so that's just going to give us pi. So now we're going to have minus pi, 0 to 1, u cubed du, so minus pi, u to 4 over 4 from 0 to 1 is minus pi over 4. So that is this whole thing, minus pi over 4. But we're subtracting at minus minus is plus. So for the final answer, plus pi over 4 is 13 pi over 20. So we have a surface integral to evaluate over a non-closed surface. We close it, use the divergence theorem on that, and then if we integrate the divergence over the solid, and then we subtract off surface integrals over the other pieces that we added to it to close it, then we get the original surface integral, which in this particular case turned out to be a whole lot easier than trying